Welcome back friends in one more video of Savind's online classes, and in this video lecture quartile deviation and coefficient of quartile deviation will be discussed. But before we start our lecture, make sure all of you are well versed with concept of median and range. If not, please pause this video here and first watch my lectures on this topic and then come back here. Measures of partition value. Because the sample range is a biased and inefficient estimate of the population range, being sensitive to extremely large and small measurements, alternative measures of dispersion may be desired. Just like median, one can also define other measures which are also known as quantiles or measures of partition value. Measures of partition are measures that divide a distribution into a specified number of parts. They are also known as fractiles, such as median, quartiles, deciles, and percentiles. We already knew that median divides a distribution in two parts, where 50% of observation remain below and remaining 50% above the median value. Similarly, quartile divides a distribution into four parts, where 25% values remain below quartile 1 or quartile 1 represent first 25 percentile, quartile 2 for 50 percentile, and quartile 3 represent 75 percentile. In the same manner, decile divide a distribution into 10 equal parts, where each part represents the 10% distribution. On the other hand, percentile divide complete distribution into 100 equal parts, where each part represents the 1% of the distribution. Quartile 2, decile 5 and percentile 50 are equivalent to median. All kinds of these partitioning value can be determined only after arranging data into ascending or descending order. However, except median, almost all other values calculated in an ascending data. What are quartiles? As we knew, a median divides a given data set into two equal halves. Similarly, the quartiles are used to divide a given data set into four equal parts. Therefore, logically, there should be three quartiles for a given distribution, but we knew that the second quartile is equal to the median itself. Therefore, we will deal with the other two quartiles in this section. The first quartile or the lower quartile or the 25th percentile, which is also denoted by Q1, corresponds to the value that lies halfway between the median and the lowest value in the distribution. Hence, it marks the region which includes first 25% of the initial data. Similarly, third quartile or the upper quartile or 75th percentile, which is also denoted by Q3, corresponds to the value that lies halfway between the median and the highest value in the distribution. Or we can say that Q3 encloses the 75% of the initial data or 25% of the end data. And this is how we can show these values in a normal distribution curve. Formulas for computing quartiles. Quartiles are located by inspection method. The series is arranged in ascending order of magnitude, and following formula is used to locate various quartile value. Quartile 1 equal to size of 1 into n plus 1 by 4th item, whereas the value for quartile 2 will be size of the 2 into n plus 1 by 4th item. In the same manner, we can also calculate quartile 3, which is equivalent to the size of the 3 into n plus 1 by 4th item, where n is the sample size. Quartile deviation. Quartile deviation is based on the difference between the first quartile and the third quartile in the frequency distribution, and difference is also known as Inter Quartle range. And this difference or Inter Quartle range divided by 2 is known as the quartile deviation or semi-interquartile range. Or in other words, when one takes half of the difference or variance between the third quartile and the first quartile of a sample distribution or frequency distribution is known as quartile deviation. This measure was proposed in 1846 by Quartile and Sir Francis Galton later called it the quartile deviation. And he also used the terms quartile and interquartile range. In addition, Sir Francis Galton developed the concept of percentiles, quartiles, deciles, and other quantiles. However, the term quantile was introduced by M.G. Kendall. Important points about quartile deviation. The quartile deviation does not take into account the extreme points of the distribution. Thus, the dispersion or the spread of only the central 50% data is considered. If the scale of the data is changed, the quartile deviation also changes in the same ratio. It is the best measure of dispersion for open-ended systems which have open-ended extreme range. Also, it is less affected by sampling fluctuation in the dataset as compared to the range, which is another measure of dispersion. Since it is solely depend on the center values in the distribution, if in any experiment these values are abnormal or inaccurate, the result would be affected drastically. The interquartile range depicts the extent to which the observation or the values of the given dataset are spread out from the mean or their average. The quartile deviation or semi-interquartile range is the majority used in a case where one wants to learn or say a study about the dispersion of the observations or the samples of a given dataset that lies in the main or middle body of the given series. Coefficient of quartile deviation. Based on the quartiles, a relative measure of dispersion known as coefficient of quartile deviation can be defined for any distribution. It can be calculated as coefficient of quartile deviation equal to Q3 minus Q1 multiplied by 100 divided by Q3 plus Q1. Since it involves a ratio of two quantities of the same dimension, it is unitless. Thus, it can act as a suitable parameter for comparing two or more different data sets, which may or may not involve quantities with the same dimensions. Quartiles and box plots. The box and whisker plots or just box plot graphically gives the approximate location of the quartiles, including the median and the extreme values. The advantage of using box plots when exploring data is that several of the characteristics of the data set, such as outliers, symmetry, feature, the range, and the dispersion of the data, can be easily compared between different groups. The lower and upper ends or hints of the box mark the 25th and 75th percentile or the location of the first and third quartile, while the solid bands indicate the median. The whisker represents the range of the values. By looking at the box and whisker plots side by side, it is possible to compare the distribution. Box plots are used to show overall pattern of response for a group. They provide a useful way to visualize the range and other characteristics of response for a large group. The diagram below shows the fashion in which bill paid during 4 days a week throughout the years. Here anyone can easily visualize range, median and interquartile distribution of bill paid during these days. Here you can also see these black dots which represent outlier. We can plot these outliers in box plot manually or through various software. We will discuss how to draw box plot in details in coming videos. Merits of quartile deviation. It is rigidly defined and it can be easily calculated and very simple to understood. This can also be used for open-end series and it does not involve much mathematical difficulties as it takes middle 50% terms, hence it is a measure better than range and percentile range. It is not affected by extreme terms as 25% of upper and 25% of lower terms are left out. Interestingly, in a moderately symmetric series, it helps in the computation of lower quartile, upper quartile, standard deviation and mean deviation in the direct manner by the models as follows. Quartile 1 is equivalent to median minus quartile deviation, whereas quartile 3 is equivalent to median plus quartile deviation. Standard deviation can be calculated by quartile deviation into 3 by 2, whereas mean deviation can be calculated by quartile deviation into 6 by 5. In case we are to deal with the center half of the series, this is the best measure to use. However, there are certain demerits or limitations also associated with quartile deviation. As quartile 1 and quartile 3 are both positional measures, hence are not capable for further algebraic treatment. Calculations are much more, but the result obtained is not of much importance. It is too much affected by fluctuation of samples. As 50% terms play no role, first and last 25% items ignored may not give reliable result. If the values are irregular, then result is affected badly. We can't call it a measure of dispersion as it does not show the scatteredness around any average. The value of quartile may be same for two or more series, or quartile deviation is not affected by the distribution of terms between Q1 and Q3 or outside each position. So going through the merits and demerit, we conclude that quartile deviation cannot be relied on blindly. In the case of distribution with high degree of variation, quartile deviation has less reliability. How to calculate quartile deviation and coefficient of quartile deviation? So now we will take some example to get a better idea of how to apply these concepts to various kind of distributions. First, we will try to locate the quartile deviation and coefficient of quartile deviation in a series of individual observations. In example 1, we have to calculate quartile deviation and coefficient of quartile deviation for the following series. First of all, we will arrange all these numbers in their ascending order. Here, the total number of observations are 15. Therefore, quartile 1 will be equivalent to 1 into 15 plus 1 by 4th item or 4th item, which is equivalent to 12. For quartile 3, it will be equivalent to 3 into 15 plus 1 by 4th item, or it will be equivalent to 12th item, which is 29 over here. After putting value of quartile 1 and quartile 3 in quartile deviation formula, we can calculate that quartile deviation for this data is 8.5. Similarly, we can also calculate coefficient of quartile deviation while putting the values of quartile 3 and quartile 1 in coefficient of quartile deviation formula, and here we can calculate the coefficient of quartile deviation for this data series is 41.46. Now we will see how to locate quartile deviation and coefficient of quartile deviation in a discrete series. There are various steps to calculate. First of all, we have to arrange the data in ascending order. Then we have to find out the cumulative frequency. Then we have to find out the values of quartile 1 and quartile 3 items by using the formula quartile 1 equivalent to 1 n plus 1 by 4th item and quartile 3 is 3 into n plus 1 by 4th item, where n stands for sample size. Then we have to find out in the cumulative frequency column which is equal or next higher to quartile 1 and quartile 3. Then we have to locate the values of these variables corresponding to cumulative frequency for quartile 1 and quartile 3. Once we know the values of quartile 1 and quartile 3, we can compute the quartile deviation and coefficient of quartile deviation. I hope all of you are well versed with the concept of cumulative frequency. If not, please watch my video on median, where I explain what is cumulative frequency and how we can make a cumulative frequency table. But we can also revise in example 2 how to make a cumulative frequency over here too, where the number of books available with 150 students are listed below, and we have to construct the cumulative frequency table for the given data. First of all, we will make a 3-column table. In first column, we will write the number of books or the value of x. In the second column, we will write the number of students or the frequency. In the third column, we will write cumulative frequency. In the first box, we will write the first frequency. In the second box, we will add this 10 with the second frequency, that is 20. 10 plus 20 will give 30. And in the same manner, we can find out the cumulative frequency for all the variables. Now we will use the same example to solve the next question. Find where we have to calculate the quartile deviation and coefficient of quartile deviation for the number of books. So first of all, we will make the cumulative frequency table. As the total number of variable or the sample size is 150 over here, therefore the value for quartile 1 will be equivalent to 1 into 150 plus 1 by 4th item, or it will be equivalent to 37.75th item. And here we can see that the 55 is the cumulative frequency in which this item will lie, and corresponding to this we can see that the number is 7. So therefore the quartile 1 value will be 7. In the same manner, we can also calculate quartile 3, and which will be equivalent to 3 into 150 plus 1 by 4th item, or it will be equivalent to 113.25th item, which will lie in 116 in cumulative frequency column. And corresponding to this, we can find out that quartile 3 will be 11 for this data set. Now after putting the values of quartile 1 and 3 in quartile deviation formula, we can find out the quartile deviation for the distribution is 2. And finally, we can also calculate the coefficient of quartile deviation by using quartile 3 and quartile 1 values, and we can calculate that 22.22 is our coefficient of quartile deviation for number of books in this data set. Let's take one more example where the weight of pod in grams of sweet peas are listed below. We have to calculate the quartile deviation and coefficient of quartile deviation of weight of pods. Like previous example, we can make a cumulative frequency table, and the sample size for this data is 200. Therefore, the quartile 1 will be equivalent to 1 into 200 plus 1 by 4th item, or it will be 50.25th item, which will lie in cumulative frequency 55, and the corresponding value will be 30, or we can say the quartile 1 will be 30 for this data. In the same manner, we can also calculate the quartile 3, which will be equivalent to 3 into 200 plus 1 by 4th item, or 150.75th item, which will lie in 153 cumulative frequency table, and the corresponding value for x is 60. Therefore, we can calculate that the quartile 3 for this data set will be 60. Now, after putting the values of quartile 3 and quartile 1 in quartile deviation formula, we can find out the 15 is the value for quartile deviation, and we can also calculate coefficient of quartile deviation with the help of these value, and in this example it is 33.33. Location of quartile deviation and coefficient of quartile deviation in a continuous series. Just like median for the case of a group data distribution, we can find the quartiles through the following step. First of all, we have to construct a cumulative frequency table for the given data alongside the given distribution. From the total number of data values, we have to estimate the groups or classes of the lower and upper quartiles, or quartile 1 or quartile 3. Following formula can be used to determine the class and group for these quartiles. And after finding out the group or class in which the quartile 1 and quartile 3 will lie, we can calculate quartile 1 and quartile 3 with the help of following formula. Quartile 1 will be equivalent to L1 plus n by 4 minus CF1 divided by FQ1 into I1, and quartile 3 will be equivalent to L3 plus 3 into n by 4 minus CF3 divided by FQ3 into I3, where L1 and L3 are lower boundaries of the classes in which Q1 and Q3 lies respectively. I1 and I3 are the class weights of the classes in which the Q1 and Q3 lies respectively. CF1 and CF3 are the cumulative frequencies preceding of the classes in which the Q1 and Q3 lies respectively. In the same manner, FQ1 and FQ3 are the frequencies of the classes in which the Q1 and Q3 lies respectively. Let's take an example to understand this concept. Where the income of 40 employees of a company is given below, we have to calculate the quartile deviation and coefficient of quartile deviation of their income. First of all, we will make a cumulative frequency table. As the sample size is 40, therefore the quartile 1 will be equivalent to 1 into 40 plus 1 by 4th item, or 10.25th item, which will lie in this class. In the same manner, we can also calculate the value for the quartile 3, which will be equivalent to 3 into 40 plus 1 by 4th item, or it will be 30.75th item, which will lie in this class. Now we can find out L1, which is the lower boundary of the class in which Q1 lies, that is 500. L3 will be 2000. I1 will be 500, I3 will also be 500, CF1 will be 6, CF3 will be equivalent to 30, FQ1 will be 7, FQ3 will be 4. Now we can calculate the value for quartile 1 and quartile 2. After putting all these values in quartile 1 formula, quartile 1 will be equivalent to 500 plus 10 minus 6 over 7 into 500, and that will be equivalent to 785.71. Similarly, for third quartile, we can calculate that quartile 3 will be equivalent to 2000 plus 30 minus 30 over 7 into 500, and that will be equivalent to 2000 only. With the help of first and third quartile value, we can calculate the quartile deviation, which is equivalent to Q3 minus Q1 over 2, or 2000 minus 785.71 divided by 2, and that will be equivalent to 607.15. Similarly, we can calculate the value for coefficient of quartile deviation, which is equivalent to the difference of first and third quartile and its ratio with their addition into 100, and that will be equivalent to 43.59. Let's take one more example, which is an inclusive series where the number of primary veins per leaf from a sample of 200 leaves from the various Ficus species are given below, and we have to calculate the quartile deviation and coefficient of quartile deviation for primary veins. Like the previous example, first of all we have to make cumulative frequency table, and the sample size or summation f is 200 over here. Therefore, the quartile 1 will be 50.25th item, which will lie in the cumulative frequency 70 or the class interval of 11 to 15. Quartile 3 will be equivalent to 150.75th item, which will lie in 177 cumulative frequency or 26 to 30 class interval. Now we can find out L1 is 11, L3 26, I1 5, I3 also 5, CF1 14, CF3 149, FQ1 56 and FQ3 is 28. In this example, we can also calculate the first and third quartile for this question, and the quartile 1 for this example will be equivalent to 11 plus 50 minus 14 divided by 56 into 5, and that will be equivalent to 14.21. Similarly, quartile 3 will be equivalent to 26 plus 150 minus 149 over 28 into 5, and that will be equivalent to 26.18. With the help of first and third quartile, we can calculate the quartile deviation, and that will be equivalent to 26.18 minus 14.21 divided by 2 or 5.99. And finally, we can also calculate the coefficient of quartile deviation, and that will be 29.64 for this question. Let's take some more example. Like if the interquartile range of a data set is given 17.56, what will be the quartile deviation of this data set? As we knew that quartile deviation is equivalent to Q3 minus Q1 divided by 2, and the interquartile range is known as Q3 minus Q1. Therefore, the quartile deviation will be 17.56 divided by 2, or it will be equivalent to 8.78. In the next example, if in a moderately symmetric series, median and quartile deviation are 35 and 8 respectively, we have to calculate the first and third quartiles as well as mean deviation and standard deviation. We knew that for a moderately symmetric series, quartile 1 is equivalent to median minus quartile deviation, quartile 3 is equivalent to median plus quartile deviation, standard deviation is a 3 by 2 quartile deviation, and mean deviation is equivalent to 6 by 5 quartile deviation. Therefore, the quartile 1 will be 35 minus 8, that will be 27. Quartile 3 will be 35 plus 8, it will be 43. Standard deviation will be 3 into 8 divided by 2, that will be 12. And mean deviation will be 6 into 8 divided by 5, that will be equivalent to 9.6. Let's take one more example where if the distribution of marks of 3 sections of a class is showing in the following box plot diagram. Based on this box plot data, we have to calculate which section have minimum marks, which section have maximum marks, and which section have on an average more marks than other, which section quartile deviation is more than other, and which section coefficient of quartile deviation is more than other. So let's take one by one. With the help of this diagram, we can calculate that minimum marks is for section C and the maximum mark will be for section B, because the whisker length is minimum in C and the whisker length is maximum in B. And the center line which is showing the median value, we can see that in these 3 sections, the median is maximum for section B. First of all, to calculate quartile deviation and coefficient of quartile deviation, we must know the quartile 1 and quartile 3 for these 3 different sections. Quartile 1 is the extreme left side of these boxes, just like for section A it is 23, section B it is 44, and section C it is 18. In the same manner, we can calculate the value for quartile 3, which is extreme right value for these boxes, and for section A it is 64, for section B it is 72, and for section C it is 34. Now we can calculate the quartile deviation for these 3 sections, and for section A it will be 64 minus 23 divided by 2 or 20.5. For section B it will be 72 minus 44 divided by 2, it will be 14, and for section C it will be 34 minus 18 divided by 2, it will be 8. For coefficient of quartile deviation, we can also put the value Q3 and Q1 in all these different sections. And the coefficient of quartile deviation for section A will be 47.13, for section B it will be 24.14, and for section C it will be 30.77. Now we can summarize the complete result, like which section have minimum marks, the answer is C. Which section have maximum marks, that is the answer is B. Which section have on an average more marks than other, that is answer B. Which section's quartile deviation is more than other, the answer will be A. And for which section's coefficient of quartile deviation is more than other, the answer will be again A. So dear friends, it is all about the quartile deviation and coefficient of quartile deviations. In the coming videos, we will also discuss other measures of partition, as well as we are about to start our new series on correlation and regression. Till then, like and share this video, press the bell icon to subscribe my channel. Jai Hind, bye bye.